Hello everyone, my name is Min Mong. I'm a technical marketing engineer for the HyperLynx high-speed analysis tools here at Mentor. Thanks for finding the time to attend today's webinar among your busy schedule. Today's topic is about customizing DDR4 designs for cost and performance. I delivered a webinar 3 weeks ago on post-layout verification of DDR4 interfaces. But this webinar will focus on the pre-layout analysis of DDR4 buses. Our goal here is to simulate early in the design cycle so that you will be confident in the post-layout verification stage that you will have expected margins. In this webinar, I'll outline the importance of pre-layout simulation for DDR4 designs running at high data rates by quoting some of Xilinx recommendations in their DDR4 design guide. I'll then recommend the overall and pre-layout DDR4 design flow. I'll then list some of electrical and physical factors you should consider for best timing and signal quality margins during the pre-layout simulation stage. I'll then provide you with some simulation results in frequency and time domain by considering the above factors for data and address buses. Finally, I'll demonstrate on how to perform some of these pre-layout simulations in HyperLynx SI. The routing guidelines provided by the controller or memory vendor are quite stringent and based on a reference stackup which affects the delays, impedance, skews, return path, and so on. But most of the time, the stackup that you will use is going to be different from the vendor's stackup. In that case, as suggested by Xilinx here, you will want to perform simulations to evaluate the trade-offs early in the design cycle. In this example, Xilinx recommends signals are routed on upper signal layers, but if you choose to route them on deeper signal layers, you will need to perform signal integrity and timing simulations. So here is the entire DDR4 design flow, but in this webinar, we'll concentrate on the pre-layout analysis portion. I've covered the post-layout verification in the previous webinar. If you missed it, I would recommend you watching it, as I also cover some of the principles behind how DDR4 design works. In the pre-layout analysis of a DDR4 interface, you will want to verify that the data bus has maximum margins running at intended data rate. In this case, the most you want to set up is 1 byte lane in the pre-layout schematic. Run both write and read simulations to derive routing constraints and optimize device settings on 1 byte lane, and you can apply those same constraints to the other byte lanes. You would also want to look at the address, command, and control bus with just one clock and one address net in a schematic to start with. You might want to look at skew requirements between the DQS and clock signals. We would like to recommend that you include the items listed in the second column here during the pre-layout design investigation. You need to design your custom stackup and vias. You will want to run simulations to know what the length matching tolerances are between the DQ and DQS net, for example. On address signals, you should investigate what the best topology is for your design, loading effects based on DRAM parts you have chosen. You also want to optimize the terminating resistor values and consider the effect of VTT voltage variation. You would also want to look at how crosstalk voltage can affect your timing margins based on the spacing you decide to use. You might also want to compare the delay and crosstalk based on which layers you route the signals on. You also want to look at how manufacturer tolerances can affect your design margins. Non-ideal PDN effects need to be investigated as well on how they affect the margins, but we'll cover these effects and simulations in a future webinar. In this webinar, we will be assuming the PDN and return path as ideal. You will also need to consider these device-related factors as shown in the third column. In your pre-layout analysis, to maximize SI and timing margins, some of these factors are using the edge rate control driver, enough drive strength to meet the timing requirements, best ODT values for data and strobe nets. You also need to include the controller and DRAM timing uncertainties in your margin calculations. You also need to know if your controller can perform leveling for DQS and clock signals and per bit calibration for both read and write or data bits. Based on this info, you will be able to make the proper design choices. For example, if your controller can perform per bit or per byte calibration, then the length matching within a byte lane doesn't need to be too stringent. Now let's discuss Stackup considerations. As I've mentioned before, the routing guidelines provided by most controller vendors are based on a reference Stackup as shown here. It also provides width, dielectric constant, and spacing for impedance, delay, and skew. But as mentioned here, if you are not using this Stackup, you must make adjustments accordingly. Now, you would need a field solver to provide you with accurate information you need. If you use a material with a lower dielectric constant, the impedance will increase and propagation delay will decrease as shown by the table here. On the left, I've entered dielectric constant as 4.7 on this layer 5 and the impedance is 32.5 and the delay is 551 picoseconds. Now by changing the dielectric constant to 3.7 but everything else kept constant, the impedance will go up to 36.6 and the delay will decrease to 488 picoseconds. In this case, we'll change the trace width and determine what the effect is on impedance, delay, and separation. On the left, I have the trace width set to 6 mils on layer 5 with dielectric constant of 3.7. The impedance is 36.6 and the delay is 488 picoseconds. If the separation is set to 3 times the width to control crosstalk, it's 18 mils. On the right, let's decrease the trace width to 5 mils. The impedance goes up to 40.5 ohms, but the delay remains unchanged. But the separation would change to 15 mils. So it's important to know that if you change a parameter on a Stackup or a trace, the impedance and delay will change. But you also need to know by how much based on your custom Stackup. Once you have determined your final Stackup by not only considering the impedance and delay, but also accounting for the return path and power delivery, you will want to plan the impedance for every layer and determine the width you will need to achieve that single-ended target impedance for every signal layer. You would also want to plan for differential impedance. It's nice to know different options along the curve for trace width versus separation to achieve that target differential impedance on each layer. Now let's talk about VIA design, which is everyone's favorite topic. With DDR4 data rates, the VIAs are not as critical as in SerDes applications in which the traces tend to run longer at higher data rates. But we want to take a look at different options so that you are not caught by surprise, as I'll show you some cases here. We'll take a look at two VIA configurations in frequency domain. The one on the top is using the micro vias, and the bottom topology is using the through-hole via with the breakout trace of 50 mils transitioning to 1 inch of trace on layer 5. The micro vias topology also transitions to layer 5. Take a look at how the 20 mils pad and 8 mils drill through-hole via is being modeled with 45 ohms barrel impedance and also 38 picoseconds delay of stub. You would need 4 microvias to transition to layer 5, but these transitions are very short in delay. If we export these two topologies with different via configurations to an S-parameter model and take a look at the insertion loss, you will notice the large resonance for the through-hole via with the stub. In this case, the resonance is around 6 gigahertz. If you look at today's highest DDR4 data rate of 4.266 gigabits per second, the Nyquist frequency is around 2.1 gigahertz, which you care about the most, then this via might not cause any issue. But if we look at the pulse response of the two topologies at 3.2 gigabits per second, you can see that the through-hole via topology performs worse with some delay push-out, ring back and overshoot due to reflections, and it takes longer to settle, which causes more ISI. Now let's take a look at the effects of via stub lengths on a 90 mils thick PCB. This schematic shows the same through-hole via transitioning to different layers deeper into the stack-up, causing different stub lengths. For example, routing on layer 3 is going to create a longer stub compared to routing on layer 12. Here we can see that the longer stub causes resonance at a lower frequency, but routing on layer 16, which is shown in green color, it does not create any resonance up to 16 gigahertz. But you can see how longer stub lengths can degrade your signal quality by looking at the pulse response. Now, if you look at the resonances with the 160 mils thick PCB with the same via transitions, the resonances are now encroaching into the frequencies that you care about. With the thicker board, the signals look a lot worse by looking at the pulse response again. So it is helpful to take a look at the via performance in frequency domain and with pulse response, which doesn't require models with pretty minimal setup and extraction time. So as in summary, we saw that the micro vias perform better than the through-hole vias. So now it's a matter of trade-offs between cost and performance. But apart from opening up the routing paths with micro vias, we also want to know how much margins you're gaining. Now let's take a look at that next. We'll first look at the address and clock bus, as it's harder to design than the data bus, since these nets route to every DRAM on a DDR4 bus. Here I have two address topologies with through-hole vias on the top and micro vias on the bottom. There are 5 loads since we're using by 16 devices for 16 data bits and by a device for the ECC bits. We'll simulate the nets running at DDR4 2.666 megatransfer per second. But note that the address bus runs at half the actual DDR4 data rates since it's clocked only at every rising edge, but the data nets clocked at every DQS rising and falling edges. We'll probe at the DRAM furthest away from the end terminator for both nets, as usually this DRAM has the worst signal quality due to reflections. You can see from the eye diagrams here with the through-hole vias on the right, you lost a little bit of timing margins, but the ringback is worse, nearing towards the AC threshold overall, reducing the noise margins. Next, let's take a look at the timing margins on this address and clock topology with microvias by varying the slew rate at the controller. With the slow slew rate driver, again looking at the DRAM furthest away from the terminator, the eye height and the width are pretty small due to the slow edge drivers. Therefore, all of the timing margins are failing, as you can see in the report. Now let's take a look at the eye at the same DRAM and the report with the medium slew rate driver. The eye is starting to open up and you now have pretty good setup and hold margins. Next, let's look at the results with the fast slew rate driver. The eye is even more open up and the margins are higher compared to the medium slew rate driver results. But using the faster driver will induce more crosstalk. Therefore, you need to make a trade-off between more margins versus more noise. Here we have this address topology with through-hole vias to see the effect of these stubs on both address and clock nets. We will sweep these lengths from 20 mils to 100 mils by locking the sweeps so that each length is swept on all traces at one time. We will look at the eye nearest to the terminator and also at the DRAM nearest to the controller. You can see that the eye looks pretty good at the DRAM nearest to the terminator for all three cases. But at the other DRAM away from the terminator, as you increase the stub length, the eye height starts to shrink. You lose some of the timing window as well, but not as significant as the shrinking of the noise margins. You need to pay attention to the ringback on the signals. In the 100 mil stub length case, the ringback is nearing the threshold shown by the blue dotted lines. If the signal starts crossing these thresholds, it can affect timing and also cause false switching in the hardware, causing intermittent problems. We will now sweep the widths on traces to see the effect on timing. I'm showing this clamshell topology with through-hole vias with 10 loads total width, 5 loads on the top layer and 5 other loads directly below. We have 10 loads instead of 5 loads because we're using the by 8 DRAM devices. So let's see if we can improve the margins by sweeping the width to vary the impedance of the traces between the DRAMs with the goal of minimizing reflections. We will vary the width from 3.5 mils to 6 mils with 0.5 mil step. These are the results with 6 mils width. The results are worse than before. The 5.5 mils width results are better, but still there are some failures. The same case is with 5 mils width. The 4.5 mils case is starting to look better, but the 4.0 mils width gives the best margins. Next, let's determine how important it is to match the relative length between the address and clock nets from one DRAM to another. Here is the more challenging clamshell topology with 10 loads case by sweeping the address net length from 650 mils to 750 mils with step size of 10 mils, but keeping the clock net's length at 710 mils. With the address net length of 650 mils, this is the failing case of the hold margin at U802, which is the DRAM on the top layer furthest away from the terminator. If we look at the waveforms, the address waveform in red and the clock waveform in blue, the address waveform is multi-crossing the low DC threshold here. but the measurement should have been here. So the worst case hold window for this DRAM is only 184.5 picoseconds. If we look at the margin calculations, we have the available window we saw in the previous slide. We subtract the uncertainties, the base hold requirement of the DRAM, and the derating factor to calculate the worst case margins for this DRAM. As we look at the other results for the passing case of 720 mils case, it has plenty of margins on the same DRAM. Now let's take a look at the waveforms. The address waveform is no longer multi-crossing the DC threshold. Now the crossing is further out and the measured hold window is now 330 picoseconds compared to 184 picoseconds in the 650 mils case. As I've demonstrated, designing the address bus is more involved, especially when more loads are added to the already complex topology. By changing the lengths between the DRAMs, you're controlling the reflections more than matching the delays. Of course, there are many cases you should look at to maximize your margins, but due to the time constraints, let's look at the data bus next. In this schematic, I have one byte lane set up with Xilinx controller and Micron DRAM IBIS models with micro vias going from top to layer 5 with trace length of 1.2 mils for all nets perfectly matched. The transition trace lengths are also all the same. I simulated this in the DDR4 wizard and looked at the eye at each DRAM with the DQS waveform overlay on top. I've only displayed here two eyes at the DRAMs with the minimum and maximum delays. Since this is a perfectly matched topology, you may ask where the skew comes from. The skew comes from the package, mostly from the controller. Now, from this simulation, you can get the maximum skew within the byte lane by making this measurement. You can also get the rough idea of what the worst setup window and hold window from these simulations. Even though the lengths are perfectly matched, the setup and hold margins are not perfectly equal due to the loading effects, the ODT value used, some signal loss, some reflections at the DRAM package, and so on. So you will need to simulate to understand how to derive the length requirements between DQ and DQS for your particular byte lane, especially if your controller doesn't perform per bit calibration. If you're routing another byte lane on another layer, you will want to investigate that case as well. Here I have the same byte lane of same length with through-hole vias. For the point-to-point topology with an ODT model at the receiver, the performance with the through-hole via is slightly even better compared to the micro via case, as you gained about 20 picoseconds on the worst case setup time in this case. But we saw that the micro vias perform better on the address signals since they are more reflective with more loads with terminator only at the end. Now let's see the effect of different drive strengths, slew rate, and ODT values on just one DQ net on the margins. We'll sweep three cases with drive strength of 40 and slow, medium, and fast slew rates with 40 ohms ODT at the DRAM. And another three cases with 48 ohms drive strength and 48 ohms ODT value at the DRAM. We will include slow and fast corner cases. So there will be a total of 12 simulation cases. Here are the results of all cases. There are some failures shown in red. Let's filter the cases which have positive margins for both slow and fast corner cases. Here's one case with ODT3 setting. From the report, we can see that the ODT3 case uses the fast slew rate driver with drive strength of 40 ohms and ODT value of 40 ohms at the DRAM. Another case that passes all requirements is ODT6 case, but the margins are slightly less than the previous case. The ODT6 case uses the fast slew rate driver with drive strength of 48 ohms. We can take a look at the eye diagram with the mask already placed. This eye uses the fast 40 ohms driver, and this one uses the fast 48 ohms driver, and note the slightly reduced margins. Now let's take a look at the effect of crosstalk on margins. We'll sweep the separation from 1 width to 3 widths with fast and medium slew rate drivers. Here are the margins with the medium driver of fast corner case without crosstalk enabled. Here are the margins with the crosstalk enabled with different separations. As you can see, crosstalk with medium driver did not make too much difference on the timing margins or noise margins. Take a look at the overlapped eyes and you can see why. Here are the margins at the DRAM with the fast driver without crosstalk. Notice both the timing and noise margins. Here are the margins with crosstalk with different separations. The timing did not get affected much, but the noise margins were reduced moderately. Again, by looking at the overlapping eyes, you can see why. Next, let's look at the timing margins by keeping the DQS length at 1.2 inch, but vary the length on the DQ net from plus or minus 200 mils with 50 mil step. Here are the results with per bit calibration off. As the data net gets shorter, the hold margin starts to shrink, and as DQ gets longer, the setup margins get smaller, especially for the slow corner case. But with the per bit calibration on with the same sweep simulation setup, you can see that the setup and hold margins are now all balanced. We use a generic algorithm to center the mask per bit. You can insert particular delay values for each bit or per byte if you have that information from your controller vendor. We have looked at many cases so far here, but finally let's talk a bit about where to probe. Is it at the die or at the pin? The JEDEC requirements are defined at the pin, but at the controller it's usually at the die. And usually the signal quality is worse at the pin for the controller since the package is significantly larger. But HyperLynx allows you to look at both pin and at the die for both cycles. Here are the margins for write at the pin on the left and at the die on the right. You can see that the margins are almost the same, with slow case slightly better at the die. Here are the margins for read with per bit calibration turn on. On the left are the margins at the controller pin, and on the right are the margins. You can see that the margins are a lot better at the die than at the pin. Now let's take a look at the eye diagrams. Here is the eye at the DRAM pin for write with calibration off. Here is the eye at the DRAM die with calibration on. You can see the eye looks slightly better. So when you have the per bit calibration turned on, it makes sense to look at the die as well. Here is the eye at the controller's pin. We'll look at the eye at the die next to compare. Here is the eye at the die, which looks a lot cleaner than at the pin. There have been cases when the signal looks better at the pin than at the die. In that case, we have to ask how much worse is it? At the end of the day, we care about the timing at the die the most. So if it is failing the margins at the die but passing at the pin, then it could be that the package models are not accurate, or the simulator had some issues with the modeling of the package, or the package is not optimized. In that case, you should contact the vendor to see if the results make sense. So just to recap, as I've demonstrated, there are many variables to consider on both address and data byte lanes. It's important to look at all these trade-offs and make these design decisions early in the design cycle so that you're not caught by surprise after the PCB is already routed. Now I would like to show you how to perform some of these simulations in HyperLynx SI. If you already have a schematic for your design in Expedition Designer, you can open the Constraint Manager to export some of these nets that you want to perform simulation on. If you have IVIS models associated in Constraint Manager and select the nets you want to export to LineSim, the models will already be assigned with proper correct pin numbers in LineSim schematic, and start with this schematic to create the topology that meets your need. Or let's say if you have a board sim file of an older version of your design that you want to redesign, let's say at a higher data rate, you could export the nets by selecting the nets in board sim and exporting them to LineSim. Once in LineSim, all the path stacks will be available from your old design, which you can modify or reuse. Now let's look at how to export S-parameter models of topologies with different vias configurations. In this case, I have 3 vias with clearance of 5 mils, 8 mils, and 10 mils. Now you export the topologies to S-parameter file. We will use the auto port mapping and set the maximum frequency you want to extract and export. Once complete in seconds, the S-parameter file is displayed in Touchstone Viewer. Take a look at the insertion loss to see the resonance moves as the anti-pad size varies due to impedance change. Next, I'll show you how to set up to look at pulse response. Set the impulse shape as trapezoidal and enter the parameters here. You can see the pulse response. The 5 mils clearance has the worst case, in this case with the minor delay push out, and takes longer to settle down. You can also take a look at the TDR impedance plot, which could provide you with more insight into your topology. Here is more challenging clamshell topology with 5 loads on the top layer and 5 loads on the bottom layer. Now let's look at this example of how to run sweeps for VTT variation in the DDRX wizard. The setup in pre-layout is same as in post-layout, except you have fewer nets to simulate here. Let's skip through some of these pages and look at where you set the driver model. We are using the controller timing parameters provided by Xilinx. The DRAM models are JEDEC compliant and ships with HyperLynx. I've set the number of bits as 128 bits. In the sweep manager page, we are set up to sweep the VTT value of plus and minus 5% with 6 millivolt of steps. We will simulate slow and fast corner cases and run the simulation. Once the simulation is done, we can open the report using the report manager. Let's scroll through the reports and you can see some failures. You can filter the report with just failures. We can see that the voltage variation can change your timing and SI margins and even cause some failures, especially on a very sensitive topology like the 10 load address nets. Now let's switch gear to look at the data byte lane 0 and simulate in the DDRX wizard to sweep with different slew rate drivers. Let's enable all of the nets in the byte lane. I have 3 different groups of driver and receiver models set up here. In the first group with the fast slew rate driver, the second group with medium slew rate driver, and third group with slow slew rate driver. From the sweep manager page, you can enable those 3 groups to sweep. We will enable both slow and fast corner cases and simulate. Filter the report and see that the first case is passing all requirements which use the fast slew rate driver. The second case uses the medium slew rate driver and they're failing the minimum slew rate margins. The slow slew rate case is failing many of the margins as we saw previously in my earlier presentation. There are 2 ways to look at the eye diagrams. These eye diagrams from the report have masks already placed on them based on the DQS edge position. The eyes with the fast slew rate are looking pretty good, and the cases with the slow slew rate driver are failing the mask. You can also import the waveforms into the oscilloscope and look at them overlapped on each other with the DQS signal. You can either take a look at the waveforms bit per bit or as eye diagrams and measure the eye width and height on each eye very easily. Finally, I would like to show you how to transfer the constraint templates you derived from the simulation to the layout engineer. You can create a constraint template here. You can create custom pin pairs by double-clicking on each pin. Open the constraint template editor to enter the constraints you derived from your simulation. You might have minimum and maximum length requirements and match length requirements. After saving the constraint template, you can pass it to the layout engineer to import it into the constraint manager of your design and apply the same template to multiple nets. And now the same constraints are applied to all nets for you to finally route the board. Now to summarize, I explained why it's important to perform pre-layout simulations early in the design cycle for DDR4 designs. I made a recommendation on the overall and pre-layout DDR4 design flow. I provided a list of electrical, physical, and device factors affecting timing and signal quality margins. I provided simulation cases in frequency and time domain, which you should care about for the data and address buses. I also demonstrated how to perform some of these simulations in HyperLynx SI. At this point, I would like to point out that we have this pre-layout workshop with all the schematic files and models I use in this webinar to get the simulation results. This workshop also contains PowerPoint file with step-by-step videos, screenshots, and narration for each section of the lab you can perform at your own pace. So if you're interested in getting your design right early in the design cycle and learn how to use these capabilities in HyperLynx SI, please click on the Contact Us link below to request for the workshop zip file. We'll send you a link for you to download. I would like to thank Syntax for letting us perform SI and timing analysis based on their design. I would also want to thank Xilinx for the controller IBIS model and timing data, which we'll provide in the workshop as well. And thanks goes out to Micron as well for letting us use the DRAM IBIS model for both demo and for the workshop. Thank you for your time today. I hope this information was useful for you. Now I would like to open up for questions.